In this tutorial, we will be looking at a simple technique to design a simple GUI. This will provide a nice graphical interface for our user, which will then allow them to change settings of the instrument, acquire data from it, and display it in a nice graphical form. The best starting point for someone who is not used to designing GUIs is to use the MATLAB feature called Guide, and we can open this by just typing Guide on the MATLAB prompt and pressing Enter. The Guide Quick Start window opens up, and from this we just select a blank GUI. Now we've got a blank canvas where we can put the elements of our GUI. Let's maximize the window first. You can see that we can decide what dimensions our GUI window will have ultimately just by changing the dimensions of the grey rectangle shown here. The first thing we'll do is go to File, then Preferences, and then in the Guide Preferences we'll tick the box which corresponds to Show Names in the Component Palette. This will allow us to identify more clearly what each element is. Then we click on Apply and then OK. Now you can see that on the menu here the name of each of the elements is shown as well as the respective icon. There are other things that we could do to modify the design environment. We could go to Tools and then Grid and Rulers, and this would allow us, for instance, to change the grid size. We'll leave it to what it is for now. And also we can decide whether we want the elements to snap to the grid or not. So let's just click on Cancel and close this. Now all the components that we see listed on the left hand side of the window are user interface controls. These are very similar to other graphic objects, but they had the advantage of being able to make the figure interactive. And just as other graphic objects, they have a set of properties that can be modified to control the object's look and behavior. The first two elements that we will be looking at are the edit text boxes, which allow you to enter data into your GUI in the form of strings, and static text boxes, which allow you to put some static text that cannot be modified by the user, on your GUI figure. Let's start with static text. So we just click on static text on the Elements menu, and then we simply draw a box right there. And then what we can do is press Ctrl+C and Ctrl+V to create copies of the box that we've just drawn. Then we can place these kind of randomly in the GUI. And then we can select them all by just clicking and dragging the mouse cursor. And then we can click on the Align Object icon up here. And this will allow us to arrange these three text boxes in a way which suits us. You can see that the Align Objects window allows you to both align elements or distribute them, either vertically or horizontally. Now the icon that shows an arrow means that that particular alignment that it corresponds to is off. So at the moment both vertical alignment and horizontal alignments are off. What we want to do is to align all our text boxes so they're effectively all in line, and we can do this by selecting Align Tops on the vertical alignment section. Then we would also like to have this text boxes distributed evenly horizontally, so we will just click on this icon here, which will allow us to distribute them based on the spacing between them, and then we can click on Apply and OK. And now the three boxes are aligned and they are spaced evenly. Now each of these boxes is an object, and objects have got properties which we can modify. We can open the property editor for each of these static text boxes simply by right-clicking and selecting Property Inspector, or by double-clicking on the element. Now you can see that the Property Inspector comes up, and you've got a number of things that you can change. The first one that we will change is the string property, and this is the text that will be displayed in the Edit Text box. So we just select the text here and delete it, and we will write center frequency in there and specify that it is in megahertz. Then we need to change another property of this object, and that is the tag. Now the tag is the most important thing to set right. because this will give us a means of accessing the object and modifying its properties from the script. And also, in the case of interactive elements, it will allow us to get the data that's been entered by the user from that specific element. It is also important to use a tag for each element, which makes it easy to identify which object it is associated with. So in this case, instead of the default text one, we will call this static text center frequency. We can then close the property inspector simply by clicking on the red cross up here, and the modifications that we've made will be saved. You can see that now on our canvas the static text box has got a different text which says center frequency megahertz. Now for the other two we can do something similar, so let's double click on the second one, and then again we'll have to change the string property so that the right text is displayed, and we'll call this one span and again specify that it is in megahertz, and then again we'll have to modify the tag and we'll call this one static text span, and then close the property inspector to save the data. Then for the third one we'll do a similar thing. We'll set the string to resolution bandwidth and the tag to static text resolution bandwidth, and then we close the property inspector. Now if we click on this icon up here, which is the object browser, we can see that under the object that represents the figure, the GUI figure, we've got some more objects, and they're all of type user interface control. And you can also see that here you've got the tag for the element shown, in this case static text center frequency, and also the string that you've set the static text box to. And you've got this for all three boxes that you've put in. So the object browser is really quite useful to check what elements you've got on the GUI and to check quickly what their tags are, for instance. So let's just close the object browser. Now the next element type that we're going to put in is edit text boxes, and these boxes allow the user to enter some data into the GUI, and this data can then be processed and used for the data acquisition or the instrumentation control. So let's just click on edit text on the menu, and then we can just draw one edit text box and press Ctrl C and Ctrl V to create 3 copies. Then we'll try to sort of align these boxes with the respective titles, and then what we can do is select these 3 boxes by just dragging the mouse cursor to encompass them all, then open the Align Object menu, turn off the horizontal alignment, and keep the vertical alignment to Align Top. Then click on Apply, and then OK. Now these 3 are perfectly aligned with one another, and then what we can also do is align the title with the respective edit text box. So we can select this pair, for instance, and then open the Align menu, and we'll turn the vertical alignment off, and we'll set the horizontal alignment to align centers, and then click on Apply, and then OK. Then we can select the next pair, and again open the Align Objects menu, and then you can see that the previous settings are saved. So again we have no vertical alignment and just align centers for the horizontal one. So we'll just click on Apply, and then OK. And we can do the same for the last pair. Now, as we did before, we need to set the properties of each of the objects associated with these edit text boxes to the right values. So we just double click on the first one, and then we scroll down to get to the string property. And this will be the default value that we want to be entered into the edit text box. So if the user doesn't enter anything, this will be the value that's in there. So we'll say that this is 2000 megahertz. And then we need to change the tag so that we can access this edit text box and get the value that the user has entered from it. We will call this tag center frequency, and we'll abbreviate it as CF. Then we just close the property inspector, and we open the property inspector for the second text box, And as a string, we will select the default value for the span, which will be 10 megahertz. And then again, we need to change the tag, and we'll call this one span. Then we do the same for the third edit text box. And again, for the string property, we will put in 1, which will be the default value for the resolution bandwidth. And then for the tag, we will use RBW. Now, the next element that we'll put on our GUI will be a pop-up menu. And the pop-up menu allows you to choose a value from a list. And this could be very useful when it comes to data acquisition and instrumentation control, because sometimes there's only so many values that are allowed in terms of parameters that we may want to set for the instrument. So let's just click on pop-up menu, and then we'll draw the pop-up menu just here. Now, this pop-up menu will be used to select the units for the resolution bandwidth, and we want to be able to select either kilohertz or megahertz. So let's just double click on this to open the property inspector. In this case, in the string field, we will have to put the various strings that will form the list from which the user can select one element. To do this, we'll just click on the list icon here, and then we delete the pop-up menu string, and we'll put kilohertz as a first string, and then megahertz as a second string, and click on OK. We'll see in a minute how this then has created a pop-up menu which comprises of two elements that can be selected, kilohertz and megahertz. In terms of tag, again, we have to choose a recognizable name, and we'll call it RBW units, and then close this. Now let's move this a little bit closer to the edit text box, and then let's move the text as well here to make it a little bit more centered on top of the two boxes. Now, as you may notice, the font is a little bit on the small side, so we'd like to be able to make the font bigger, and we would like to do this for all the elements on the figure. We can either just click and drag with the mouse to select all the elements on the figure, or quite simply we can press Ctrl A and this will select them all. And now what we're able to do is right click on this group of objects and open the property inspector, and this will allow us to change any of the properties which are common to all of the elements selected in one stroke. So for example, when it comes to the font size, we could simply type in 12, and this will change the font size for all the elements on the figure. Let's not forget that our GUI figure is also an object, and so we can just right click on the canvas and select Property Inspector, and this will allow us to change the properties of the actual figure on which all the other objects are placed. So for example, we could choose the color to be light blue, and then we could also select all the static text boxes and then right click on any one of them, open the property inspector, and then change the color to something other than this dull gray. Let's say that we choose this one here and click on OK. Now we may also want to insert something that allows us to display the data that we've acquired from the instrument in a graphical form, and we can do this by inserting some axes. So again, we can just click on axes here and then draw them on the figure. We can double click on this element and change its properties. There's a number of properties that can be changed. As you know, the one that we are really interested in is the tag property, and this is set to axis 1. This is really quite recognizable, and we can leave it to what it is for now, because we'll only have one set of axes on this GUI. So let's just close the property inspector. Lastly, we want to insert a push button. So let's just click on push button here, and then draw one right next to our axis. We will use this button to allow the user to start the acquisition once all the parameters that the instrument needs to be set to have been selected. So we double click on this push button here, we'll change the string property to acquire. Then in terms of tag, we can also change the tag to acquire, although in this case we only have one push button, so there wouldn't be much of an ambiguity there. And the last thing that we may want to do is change the font size to 12 to match the font that we've selected for the other objects on the GUI. So now we've taken care of most of the graphical aspects of our GUI. What we can do now is save it. So we just click on the save icon and we'll call this one Basic GUI. Now what happens when you save the GUI is that a full script gets generated, and this is the code which operates behind the GUI. The first bit of this code, as clearly specified in the comments inserted by MATLAB, is not to be edited. Then you have an opening function for the GUI, which is very, very important, and we will be talking about this opening function and what it allows us to do later on. Then, for most of the elements which we have placed in our GUI figure and which involve interaction with the user, for example the edit text boxes, MATLAB has created two functions, a callback function and a create function. To figure out which element this pair of functions is associated with, you just need to look at the function names, which start with the element tag. For example, remember that we set a tag equal to CF for our center frequency edit text box, and hence the callback and create function that are shown here are connected to that specific element, to the edit text box for the center frequency. So the first function, the CF underscore callback, is the function that contains the code that needs to be run when the user modifies or interacts with the center frequency edit text box. And this code is run automatically when there is some interactions with the center frequency edit text box. The create function instead allows you to modify the graphical properties of the element. You can modify and change the appearance of an element through this function, but it is usually easier to just modify the appearance of an object directly on the GUI figure and then save it, and MATLAB will then modify the create function accordingly. The callback functions are the ones that you should focus on once the script has been created, since they allow you to define which actions should be taken when the user interacts with a user interface control, in this case the center frequency edit text box. We can see that for most of the elements which allow the user to enter some data, two functions are created in a similar fashion, with the names that start with the tag of the respective element. You can see that we have a callback and a create function for both span and resolution bandwidth, and also there's a similar pair of functions for the resolution bandwidth units. Now, if we look at the very last callback function, which is relative to the push button, remember that we set a tag equal to acquire for a push button object, you can see that there is only one function, only the callback function, there's no create function. And this is just the way that the push button element works in Guide. So let's go back to the callback, which corresponds to our first edit text box, center frequency, with the tag CF. There are three parameters which are passed to this function, and these will be the same for all of the callback functions in this example. The first one is hObject, which is the handle to the object which represents the center frequency edit text box, and it allows you to modify its properties as well as getting data from it, such as the value which is entered in the box. The event data variable is reserved, and hence you need not concern yourself with it. Now, the third one is extremely important, and is a very clever way to handle all the objects that are on your GUI figure and also all the data that the user may enter. Remember that what we put on a GUI figure are all object type elements, and what you need to access any object type element is an object handle. You can think about a handle as the handle to a large drawer full of compartments. The handle allows you to open the drawer, and then all the compartments will be the properties of the object. The handle in the case of MATLAB objects is a unique number that is assigned to an object when it is created, and it allows you to access it anytime. So when you run the script which MATLAB has created behind the GUI, the first thing that MATLAB will do is assign handles to each of the objects that are on the GUI figure, and then it will store them all into one single structure called handles, which is the one that we're passing to our function here. Now, in the structure handles, each of the object handles will be identified by the tag of the object that it refers to. And these handles allow you to modify any of the elements and get data from the interactive ones, like edit text boxes. So handles is very useful to get access to any of the objects on the GUI figure. But the other thing that we can do, which is extremely useful, is to add elements to the structure which will contain the data that the user has entered. It is an excellent idea to keep all the handles of the objects in the GUI figure and all the data that comes from them in one structure. Then we can pass the structure to each function, which can modify it or add to it and then return it. This will become clearer as we run the script. The other thing that MATLAB does is to put useful comments in our callback function, which will give us hints as to how to carry out tasks which we are likely to want to carry out. For example, it tells us, in the case of an edit text box, how to get the text from it. So we've interacted with our center frequency text box, and the respective callback function is called. So what we may want to do, because something has happened in the box, for example the user has entered new data, is to get this data and store it in a variable. Now, to read the value which has been entered in the box, the hint tells you that you can just use the get command. The get command is quite simple. You're just basically saying to MATLAB, go to the object whose handle is contained in the variable h object, which in this case is our center frequency text box, and get me the value of the property string of this object. And the string property is the property in which the value entered by the user is stored. So we will just take the hint. So let's copy and paste this bit of code, and now of course we'll have to assign the value that's returned by the get function to some sort of variable. You can declare a new element within the handle structure with the dot syntax. For example, you could write handles.new data equals 1000, and this will create an additional element in the handles structure which you can then access. So we can use the syntax handles.cf_string equals get from h object the value of the property string. So what we've done here is basically add an element to the handles structure which is called cf_string. And then we've assigned the string entered by the user into the edit text box to this variable. Now you may argue that because we're inside a function, we won't be able to access this variable from the global environment. And this is true. What we need to do is to use the function GUIData to update the values in the structure handles in a global manner and make them accessible globally. The syntax for this is shown here. This line of code will be the final line of code for most of our callback functions, since it allows us to then pass the structure handles as has been modified by the function back to the main script. Now what we need to do is write similar code for all of the callback functions which are connected to an edit text box. So for example, for the span callback function, what we'll do is declare a variable called handles.span_string, and then we will assign the value returned by the get function to this new element that we've inserted into the handles structure. And then we will update the handles structure globally. For the resolution bandwidth, we'll do a similar thing. We will add a variable to the handles structure called rbw_string, and we will assign the value returned by the get function to it. And then we will update the handles structure globally. So what's going to happen is that every time the user interacts with any of the edit text boxes on the GUI figure, the relative callback function will be called, and the value that's been entered by the user will be stored in the handles structure. Now, in the case of a pop-up menu, things are slightly different. As we have seen earlier, in this case we have provided the user with a selection of two strings, which he may choose between. Each of these strings has a number associated with it. The first one, kilohertz, is number 1, and the second one, megahertz, is number 2. To find the number that corresponds to the string which the user has chosen, we can use the code shown here. We can use the get function on the object hObject, which in this case represents the pop-up menu, and from this object we can get the property value. This represents the number which is associated with the string that the user has chosen. We can assign the value returned by the get function to a local variable val. Now we can also get the list of strings from the object. So we'll use the get command once again, and this time from our pop-up menu we will require the value of the property string. The function get in this case will return an array of two strings which we will store in the local variable string_list. Now, string list is a 1×2 vector, and the first element will be the string kilohertz and the second element will be the string megahertz. Now, which one of these elements has been selected is identified by the value of the variable val. So if we use val as the index of the cell of the string list array, then we should get the string that the user has selected. And this is just what this instruction shows. String list of val will give us the element from the string list which the user has selected, and we store it yet again in a variable as part of the handles structure, which is called rbw_units_string. Then, as we usually do, we update the structure handles globally so that the data that is stored in it can be accessed globally. The last callback that we need to discuss is the one associated with the push button identified by the tag acquire. When the user clicks on the acquire push button, the acquire callback function will be called. What actions do we want to take now that the push button acquire has been pressed? Well, first of all, we want to set up the instrument using the parameters which the user has entered, and then we would like to start the data acquisition. So this is where we need to write the code which sets up the instrument and carries out the data acquisition, and then of course also the code that will allow us to display data on our GUI figure. So we are now going to run the GUI script, but before we do so we will put some strategic breakpoints inside the callback functions so that we will be able to see in detail what happens when any of these functions get called. Inserting breakpoints in MATLAB is quite easy. You just click on the left-hand side of the line of code where you want your breakpoint, and you should see a circle appearing. This circle will be grey if the code has not been saved, and it will be red if the code has indeed been saved. The advantage of having breakpoints is that this also allows you to see what happens to the variable as you're running the script, because you can just hover over any variable with the mouse cursor and you will see what value that variable currently has. So let's click on the play button at the top of the script and you can see that the GUI figure appears. Now here we have to talk a little bit about the data flow when it comes to GUIs. When you run the GUI, the first thing that MATLAB does is to draw the GUI figure. The next thing that MATLAB does is to create the handles structure. The handles structure at this stage will contain all the object handles which refer to all the elements which we've placed on our GUI figure. So, first step, drawing the GUI. Second step, creating a structure called handles which contains all the object handles to every single element that you see on the GUI figure. The next thing that MATLAB does is run the opening function. At the moment we haven't got any bespoke code in there, so this doesn't really make much of a difference at this stage. And then MATLAB waits for user action. So it has drawn the GUI, it has created the handle structure, and then it has run the opening function. Now it's waiting for the user to do something with the user interface controls. So for example, let's change the center frequency from 2000 to 1000. Now we can either press enter or simply click on another box. Let's just press enter. Now the callback function that corresponds to the center frequency edit text box gets called. As we mentioned, the great thing about running things this way is that now I can hover over with the mouse on any of the variables and I will see what values they have. Let's start with the handles structure. Now you can see that in the handle structure at the moment we've got object handles to absolutely everything in our GUI. For example, you can see that the handle for our center frequency edit text box, which has got CF as a tag, is 2.0013. Event data we won't have to bother with. HObject, as we've said, is the object handle which corresponds to the element whose callback function has been called. And you can see that this is indeed the case because HObject is 2.0013, which is exactly what handles has shown us to be the object handle of the center frequency edit text box. So now, if we step through the code, which we can do by pressing F10, we can see that now the structure handles still has all the object handles just as they were, but at the very bottom there is an extra variable that's been added, and the CF underscore string, and this is equal to 1000, which is the value that we've just entered in the box. Next, we press F10 yet again to execute the last line of code, which will then update the structure handles globally and make the new variable that we've added available to any of the other functions or any other part of the script. So now that the callback function has been fully executed, MATLAB goes back yet again into a state where it's waiting for the user to interact with the GUI yet again. So for example, let's go to the span and change its value to 1. Then instead of pressing enter, we can just click on another box. This also triggers the callback function relative to the edit text box span to be called. Now if we hover over the structure handles with the mouse, we can see that yet again we have all the object handles as we did at the very beginning, but also the CF underscore string variable, which was added by the CF callback function. So you can see why using the GUI data function at the end is important, because it allows the modifications that we make to the structure handles to be available globally. You can also see that the handle corresponding to the span edit text box is 3.0013. And if we hover over HObject with the mouse cursor, we should see that this is the value that this variable has, because of course we are in the callback function for the span. Now if we press F10 to execute the line of code that is currently pointed out by the arrow, and then we hover over handles with the mouse cursor, we can see that an extra variable has been added to the structure, which is span underscore string, and this has the value that the user has entered. Yet again we have to execute the last line of code as well, which will update the structure handles globally. Now that the callback function for the span has been fully executed, MATLAB is yet again waiting for the user to interact with the GUI figure. Let's change the resolution bandwidth from 1 to 0.1 and press enter. Now the resolution bandwidth callback function gets called. If we hover over handles with the mouse, we can see that the data entered by the user previously has been saved in the CF underscore string and span underscore string variables. We can also see that the object we tag RBW, which is our resolution bandwidth edit text box, has got a value of 4.0013, and this should be the same as HObject. Now yet again we execute the code by stepping through it with F10, and then we can see that the rbw_string variable has been added to the handles structure, and once we execute the last line of code in the function, this data will be available globally. Now let's go back to our GUI yet again. MATLAB is waiting for us to do something else, and what we'll do is change the resolution bandwidth to megahertz. The resolution bandwidth units callback function gets called. We can see yet again that all the previously entered values are all saved in the structure handles, and now we can execute the code bit by bit to recover the string that's been selected by the user. The first thing that we do is recover the number which corresponds to the string that has been selected, because in this case we selected the second string. Val should be equal to 2. So let's step through this line of code, hover over val, and this should have a value of 2. Then we need to get the string list from the object, and this should be a vector with 2 components. The first one will be the string kilohertz, and the second one the string megahertz. Then we execute the next line of code to recover the string by using the array that we've just acquired, combined with the number corresponding to the string number that the user has selected, which will be stored in val. And this gets us the right units, which is the units of megahertz, and stores them into the handles structure. We execute the last line of code to get things updated globally, and we're done. Now it's time to talk a little bit about the opening function. As we said, when we run the GUI, the first thing that MATLAB does is it draws the relative figure. Then it creates the handle structure, and then it runs the opening function. The opening function is very useful to initialize the variables which will be used to store the data which is entered into any of the user interface controls on the GUI. Despite the fact that for each of the edit text boxes on our GUI we have set an initial string which represents the default value for the parameter of the respective edit text box, when the GUI is launched, these default values will not be automatically taken in and assigned to the right variable. What we have to do is make specific declarations and add specific instructions in the opening function so that all the variables are initialized and none of the relevant variables are assigned to random values. This is relatively easy because we can just use the code from our callback functions to make these initial assignments. For example, we can go to our center frequency callback function and we can just copy this line of code from here into our opening function. However, we have to be very careful with this sort of thing, because when we were inside the CF callback function, then HObject represented the object handle to the center frequency edit text box. However, here HObject represents the handle to the figure, as is clearly stated in the comments shown here. So we can't use HObject in this case to get the value contained in our center frequency edit text box. But this is not a problem, because we saw earlier that the handles structure contains the handles for all the elements on our GUI. So instead of HObject here, what we can put is handles.cf, because this variable gives us the handle to the center frequency edit text box. We can do the same for all of the other edit text boxes. So for the span, for example, we will just need to replace HObject with handles.span, and for the resolution bandwidth we'll have to replace HObject with handles.rbw. You can see now why it is very important to assign recognizable tags to our elements. To initialize our pop-up menu we'll have to copy a little bit more code because it's 3 instructions that we need. And of course we'll have to replace HObject in 2 places with handles.rbw_units. Finally, as usual, we'll have to use the GUI data function to update the handles structure globally. So now we're done with our opening function. we have declared and assigned initial values to all the variables that we'll need to store the data that the user enters. Now what is left to do is to go down to the push button callback function, which is called acquire_callback, and define the actions to be taken when the user clicks on this push button. So what do we want to happen when the button is pressed? First of all, we'll want to create a connection with the instrument. And we can do this quite easily, as we have seen in previous tutorials. We can just create an interface object and connect to it, and then look at the code in the session log and copy and paste it right here to create our connection and open the interface object to allow bidirectional communication. Then we need to set the values of the instrument parameters to the values entered by the user. We will be looking at this code in more details shortly as we go through it step by step whilst running the script. Now that we've connected to the instrument and we've set it up, we need to put in the code for the data acquisition. We will not be going through the code in great detail because it is very similar to the code that we've used for other instruments and that is shown in the book and in other tutorials. It is just modified slightly to suit the specific instrument which we are using here, which is a Rohde-Schwarz signal analyzer. Lastly, we want to insert some code which will allow us to display the data which we've acquired. Again, we will be going through this code in more detail as we do a step-by-step run. So let's save our script now and just run it without breakpoints. So we'll just click on the play button, and then we will set up our instrument first of all. The signal that we've set up is a pulse RF signal with a carrier frequency of 500 MHz and a modulation frequency of 10 kHz. We will be looking at the spectrum of this signal, which will of course be centered around the RF carrier frequency, which is 500 MHz, and hence we'll set the center frequency to 500 MHz. Then we'll select the span to be 1 MHz and start with a resolution bandwidth of 100 kHz. As you can see, the spectrum at the moment is quite dense, and that is because the resolution bandwidth is a little too large, and hence we need to reduce it to see the spectral components as distinct. If we set the resolution bandwidth to 10 kHz and then we run the acquisition again, we can see that the spectrum is now displayed in more detail and individual spectral components are more clearly identifiable. Now let's try to zoom in a little by selecting the span to be 0.1 MHz and the resolution bandwidth to be 1 kHz. You can see that now we are seeing a very detailed picture of a small portion of the spectrum. Now let's go back to the script and put in a couple of breakpoints. The first one in the opening function and the second one at the beginning of the acquire callback function. So as we mentioned, when this script is run, first the GUI is drawn and then the handles are created. After that, the opening function is run. So now when we run the script, of course the opening function will be called, and because we've inserted a breakpoint there, we'll end up right at that breakpoint before we can do anything else. If we hover over handles with the mouse, we can see that all the object handles are in there. Then of course we go through the initialization of all the variables that we will use to store the user data, and then these variables and the initial values that we've assigned to them are saved within the handles structure. Now let's continue running the script by pressing F5. Of course, we've completed the execution of the opening function, and hence now we're back to the GUI figure where MATLAB is waiting for the user to interact with any of the user interface controls. So let's set the center frequency to 500 MHz, the span to 1 MHz, and the resolution bandwidth to 10 kHz, and then click on Acquire. Of course, we've got a breakpoint in the acquire function, so when it gets called, we get the chance to step through it. The first bit is, of course, the code for the instrument connection. So that's really quite straightforward. We've spoken about that before, and we don't need to go through it in any detail. The next bit of code concerns the instrument setup. Some of the commands are just commands that we would always start with. For example, we'll reset the instrument to its initial state. And then, of course, we need to set some of the parameters of the instrument to the values that the user entered. For example, to set the center frequency, we create the center frequency command by using string concatenation. So we're concatenating the command syntax that we already know with the value of the parameter that we want to set the center frequency to. Of course, you can see that in this particular instance, when it comes to instrumentation control and creating strings to send to the instruments, having the data that is being entered by the user stored into strings is very useful, because if it was stored into variables of type double or something along those lines, then we'd have to carry out a conversion between a number and a string. In this case, instead, we can just use the string directly in the command, and hence it's better to keep the values entered by the user in string format for a lot of the work that we do in instrumentation control. However, if we had to manipulate the value that the user has entered before sending the command, then we would have had to use the string to num and num to string commands to do the appropriate conversions. We could also be more concise and not use an intermediate variable as we've done for the center frequency. We could do what we've done for the span command and send the concatenated string directly to the fprintf function. But the problem with this is that if you do a step-by-step execution, for example when you're debugging, then you won't be able to hover over with the mouse and see what the actual string has turned out to be. So it's always best to create a string which represents the command and store it into a variable first, and that way we'll be able to check what it actually is, and then pass this variable to the fprintf function to send it to the instrument. Now, the next bit of code we don't need to go through, because it's just a specific code that is used to acquire the data from the instrument, and it is similar to stuff we've done before. Is not the object of this particular tutorial. So we can just click on the next instruction that we want to step through, and then go on to the debug menu and say go until cursor. This way the script will be executed up until the point where the cursor currently is, which is the point where we want to stop and run the code step by step again. So you can see now that we've got two variables, x frequency, gigahertz, and data, which represent the x and y coordinates of all the points that we want to plot. Notice in this case how the plot function is used slightly differently to what you're probably used to, because you're specifying the place where you want the data to be plotted. So before you give the function the x and y data, you need to specify the destination, and this is done by adding an initial parameter, which is an object handle, and it represents the handle to the axis object that we've put on our GUI figure.